Chapter 3. Mathematics in Aviation Maintenance. Introduction. Mathematics is woven into many areas of everyday life. Performing mathematical calculations with success requires an understanding of the correct methods, procedures, practice, and review of these principles. Mathematics may be thought of as a set of tools. The aviation mechanic needs these tools to successfully complete the maintenance, repair, installation, or certification of aircraft equipment. Many examples of using mathematical principles by the aviation mechanic are available. Tolerances in turbine engine components are critical, making it necessary to measure within a 10,000th of an inch. Because of these close tolerances, it is important that the aviation mechanic can make accurate measurements and mathematical calculations. An aviation mechanic working on aircraft fuel systems also uses mathematical principles to calculate volumes and capacities of fuel tanks. The use of fractions and surface area calculations are required to perform sheet metal repair on aircraft structures. 3-1. Quotient divisor dividend. Example. 218 landing gear bolts need to be divided between 7 aircraft. How many bolts will each aircraft receive? 31. To 7,218. As minus 21. To 8. Minus 7. Place value. Tens. Whole numbers. Whole numbers are the numbers 0, 1, 2, 3, 4, 5, and so on. Whole numbers can be thought of as counting numbers. Addition of whole numbers. Addition is the process where the value of one number is added to the value of another. The result is called the sum. When working with whole numbers, it is important to understand the principle of the place value. The place value in a whole number is the value of the position of each individual digit within the entire number. For example, in the number 512, the 5 is in the hundreds column, the 1 is in the tens column, and the 2 is in the ones column. Examples of place values of 3 whole numbers are shown in figure 3-1. When adding several whole numbers, such as 4,314, 122, 93,132, and 10, align them into columns according to place value and then add 4,314, 122, 93,132 plus 10, 97,578. Therefore, 97,578 is the sum of the 4 whole numbers. Subtraction of whole numbers. Subtraction is the process where the value of one number is taken from the value of another. The result is called t-difference. When subtracting 2 whole numbers, such 3,461 from 97,564, align them into columns according place value and then subtract. 97,564-3,461, 94,103. The difference of the 2 whole numbers is 94,103. Multiplication of whole numbers. Multiplication is the process of repeated addition. For example, 4 times 3 is the same as 4 plus 4 plus 4. The result is called the product. Example. How many hydraulic system filters do you have? If there are 35 cartons in the supply room and each carton contains 18 filters? 18 times 35, 90, 54, 630. Therefore, there are 630 filters in the supply room. Division of whole numbers. Division is the process of finding how many times one number, called the divisor, is contained in another number, called the dividend. The result is the quotient, and any amount left over is called the remainder. 1. In this case, there are 31 bolts for each of the 7 aircraft with 1 extra remaining. Fractions. A fraction is a number written in the form n/d where n is called the numerator, and d is called the denominator. The fraction bar between the numerator and denominator shows that division is taking place. 17 to 5. Some examples of fractions are 18, 3, 8. The denominator of a fraction cannot be a 0. For example, the fraction 2/0 is not allowed, because dividing by 0 is undefined. 10,000s, thousands, hundreds, ones. 35 shown as 3, 5. 269 shown as 2, 6, 9. 12,749 shown as 1, 2, 7, 4, 9. Figure 3-1. Example of place values of whole numbers. 3-2. 15/8 are examples of improper fractions. Finding the least common denominator. Equals. 193. Equals 1. 88 plus. 3, 5, 7. 105, 105, 105, 105, 105. Multiplication of fractions. Addition of fractions. An improper fraction is a fraction in which the numerator is equal to, or larger than the denominator. For example, 4/4 or 3, 1, equals 3 times 2, 1, equals 6, 1, equals 6 plus 1, equals 7 plus 32, 64, 32 times 2, 64. 64, 64, 64, 64. Therefore, 7/64 is the total thickness. To add or subtract fractions, they must have a common subtraction of fractions denominator. In math, the least common denominator, LCD, to subtract fractions, they must have a common denominator. is generally used. One way to find the LCD is to list the multiples of each denominator, and then choose the smallest example. Subtract 2/17 from 10/17. Number that they all have in common can be divided by 10 to 10 minus 2 8 minus equals example. Add 1/5 plus 1/10 by finding the LCD. 17, 17, 17, 17. Multiples of 5 are 5, 10, 15, 20, 25, and so on. Multiples of if the fractions do not have the same denominator, then 1 or 10 are 10, 20, 30, 40, and so on. Notice that 10, 20, and 30 all the denominators must be changed so that every fraction are in both lists, but 10 is the smallest for LCD. The advantage has a common denominator of finding the LCD is that the final answer should be in the simplest form. Example. The tolerance for rigging the aileron droop of an airplane is 7/8 inch plus minus sine 1/5 inch. What is the minimum droop to? A common denominator can also be found for any group of which the aileron can be rigged. To subtract these fractions by multiplying all the denominators together. This first change both to common denominators. The common number is not always the LCD, but it can still be used to add denominator. In this example is 40. Change both fractions to or subtract fractions. 1/40, as shown, then subtract. Example. Add 2/3 plus 3/5 plus 4/7 by finding a common denominator. A common denominator can be found by multiplying the 7, 1, equals 7 times 5, 1 times 8, equals 35, 8, equals 35 minus 8, 27 minus equals 8, 5, 8 times 5, 5 times 8, 40, 40, 40, 40. Denominators 3 times 5 times 7 to get 105. Therefore, 27/40 is the minimum droop. 2, 3, 4, equals 70, 63, 60. Multiplication of fractions does not require a common denominator. To multiply fractions, first multiply the numerators. Then, multiply the denominators. In order to add fractions, the denominators must be the same number. This is referred to as having common denominators. Example. Example. Add 1/7 to 3/7 3/7. 1 3 times 7 times 1 21 times equals 5 8. 2 5 times 8 times 2, 80. 1 3, 1 plus 3 4 plus equals 7, 7, 7 7. The use of cancellation, when multiplying fractions, is a helpful technique. Cancellation divides out or cancels all if the fractions do not have the same denominator. Then one or common factors that exist between the numerators, and all the denominators must be changed so that every fraction denominators, when all common factors are cancelled before, has a common denominator. The multiplication, the final product, is in the simplest form. Example. Find the total thickness of a panel made from example 3/32 inch thick aluminum that has a 1/64 inch thick paint 2, 1 coating. To add these fractions, determine a common denominator. The LCD for this example is 1. So only the first fraction must be changed since the denominator of the 14, 15 times 3 equals 14, 7, 15 times 3 equals 2 times 1 equals 7, 5 times 1, 2, 5, 5. 1 second fraction is already in 6/4 ths. 3-3 divided by 2, 1 equals 87, 16 equals times 1, 2 equals division of fractions. Division of fractions does not require a common denominator. To divide fractions, first change the division symbol to multiplication. Next, invert the second fraction. Then, multiply the fractions. Example. Divide 7/8 by 4/3. 7, 4 equals 7, 3 equals 7 times 3, 21 divided by times equals 8, 3 8 4, 8 times 4, 32. Example. In figure 3-2, the center of the hole is in the center of the plate. Find the distance that the center of the hole is from the edges of the plate. To find the answer, the length and width of the plate should each be divided in half. First, change the mixed numbers to improper fractions. 5 and 7/16 inches equals 87/16 inches. 3 and 5/8 inches equals 29/8 inches. Then, divide each improper fraction by 2 to find the center of the plate. 87, 16, 87 inches 32, 29, 8. Divided by 2, 1, 29, 8, 1, 2, 29 inches 16. Finally, convert each improper fraction to a mixed number. 87 equals 87 divided by 32 equals 2. 23 inches 32, 32. 29 equals 29 divided by 16 equals 1. 13 inches 16, 16. Therefore, the distance to the center of the hole from each of the plate edges is 2 and 23/32 inches and 1 and 13/16 inches. 3, 5, 8, 12, 5, 7, 16. Reducing fractions. A fraction needs to be reduced when it is not in the simplest form or lowest terms. Lowest term means that the numerator and denominator do not have any factors in common. That is, they cannot be divided by the same number or factor. To reduce a fraction, determine what the common factors are and divide these out of the numerator and denominator. For example, when both the numerator and denominator are even numbers, they can both be divided by 2. Example. The total travel of a jack screw is 13/16 inch. If the travel in one direction from the neutral position is 7/16 inch, what is the travel in the opposite direction? 13/7. 13 minus 7 6 minus equals 16. 16. 16. 16. The fraction 6/16 is not in lowest terms, because the numerator, 6, and the denominator, 16, have a common factor of 2. To reduce 6/16, divide the numerator and the denominator by 2. The final reduced fraction is 3/8 as shown below. 6 divided by 2, 3 equals 16. 16 divided by 2, 8. Therefore, the travel in the opposite direction is 3/8 inch. Mixed numbers. A mixed number is a combination of a whole number and a fraction. Addition of mixed numbers. To add mixed numbers, add the whole numbers together. Then add the fractions together by finding a common denominator. The final step is to add the sum of the whole numbers to the sum of the fractions for the final answer. Example. The cargo area behind the rear seat of a small airplane can handle solids that are 4 3/4 feet long. If the rear seats are removed, then 2 1/3 feet is added to the cargo area. What is the total length of the cargo area when the rear seats are removed? 4. 3 plus 2, 1 equals 6. 13 equals 4 plus 2 plus 3 plus 1 equals 6 plus 9 plus 4 equals 4. 3, 4, 3, 12. 12. 7. 1 feet of cargo room 2. Subtraction of mixed numbers. To subtract mixed numbers, find a common denominator for the fractions. Subtract the fractions from each other. Figure 3-2. Center hole of the plate. 3-4. May be necessary to borrow from the larger whole number when subtracting the fractions. Subtract the whole numbers from each other. The final step is to combine the final whole number with the final fraction. Example. What is the length of the grip of the bolt shown in figure 3-3? The overall length of the bolt is 3 1/2 inches, the shank length is 3 1/8 inches, and the threaded portion is 1 5/16 inches long. To find the grip, subtract the length of the threaded portion from the length of the shank. 3 1/8 inches minus 1 5/16 inches equals grip length. To subtract, start with the fractions. Borrowing is necessary, because 5/16 is larger than 1/8, or 2/16. From the whole number 3, borrow 1, which is actually 16/16. After borrowing, the first mixed number is now 2 18/16. This is because 3, 1 divided by 8 equals 3, 2 divided by 16 equals 2 plus 1 plus 2 divided by 16 equals 2 plus 16/16 plus 2 divided by 16 equals 2 18/16. 3, 1 minus 1, 5 3, 2 minus 1, 5 equals 2, 18 minus 1, 5 equals 1, 13 equals 8, 16, 16, 16, 16, 16, 16. Therefore, the grip length of the bolt is 1 13/16 inches. Note, the value for the overall length of the bolt was given in the example, but it was not needed to solve the problem. This type of information is sometimes referred to as a distractor, because it distracts from the information needed to solve the problem. The decimal number system. Origin and definition. The number system that we use every day is called the decimal system. The prefix in the word decimal, dec, is a Latin root for the word 10. The decimal system probably originated from the fact that we have 10 fingers, or digits. The decimal system has 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. The decimal system is a base 10 system, and has been in use for over 5,000 years. A decimal is a number with a decimal point. For example, 0.515, 0.10, and 462.625 are all decimal numbers. Like whole numbers, decimal numbers also have place value. Millions, hundred thousands, 10,000s, thousands, hundreds, tens, ones, tenths, hundredths, thousands, 10,000ths. 1,623,051, 1, 6, 2, 3, 0, 5, 1. 0.0531, 0, 0, 5, 3, 1. 32.4, 3, 2, 4. Figure 3-4. Place values. Place value. The place values are based on powers of 10, as shown in figure 3-4. Addition of decimal numbers. To add decimal numbers, they must first be arranged, so that the decimal points are aligned vertically and according to place value. That is, adding tenths with tenths, ones with ones, hundreds with hundreds, and so forth. Example. Find the total resistance for the circuit diagram shown in figure 3-5. The total resistance of a series circuit is equal to the sum of the individual resistances. To find the total resistance, RT, the individual resistances are added together. RT equals 2.34 plus 37.5 plus 0.09. Arrange the resistance values in a vertical column, so that the decimal points are aligned and then add 2.34 37.5 plus 0.09 39.93. Therefore, the total resistance, RT equals 39.93 ohms. 2.34 ohms. Shank. Grip. 37.5 ohms. M. 0.09 ohms. Overall length. Figure 3-3. Bold dimensions. Figure 3-5. Circuit diagram. 3-5. Subtraction of decimal numbers. To subtract decimal numbers, they must first be arranged, so that the decimal points are aligned vertically and according to place value. That is, subtracting tenths from tenths, ones from ones, hundreds from hundreds, and so forth. Example. A series circuit containing two resistors has a total resistance, RT, of 37.272 ohms. One of the resistors, R1, has a value of 14.88 ohms. What is the value of the other resistor, R2? R2 equals RT minus R1 equals 37.272-14.88. Arrange the decimal numbers in a vertical column, so that the decimal points are aligned and then subtract. 37.272-14.88, 22.392. Therefore, the second resistor, R2 equals 22.392 ohms. Multiplication of decimal numbers. To multiply decimal numbers, vertical alignment of the decimal point is not required. Instead, align the numbers to the right in the same way that whole numbers are multiplied, with no regard to the decimal points or place values, and then multiply. The last step is to place the decimal point in the correct place in the answer. To do this, count the number of decimal places in each of the numbers, add the total, and then assign that number of decimal places to the result. Example. To multiply 0.2 times 6.03, arrange the numbers vertically and align them to the right. Multiply the numbers, ignoring the decimal points for now. 6.03 times 0.2. 1206. Ignore the decimal points, for now. After multiplying the numbers, count the total number of decimal places in both numbers. For this example, 6.03 has 2 decimal places, and 0.2 has 1 decimal place. Together there are a total of 3 decimal places. The decimal point for the answer is placed 3 decimal places from the right. Therefore, the answer is 1.206. 6.032 decimal places times 0.21 decimal place. 1.2063 decimal places. Example. Using the formula watts equals amperes times voltage. What is the wattage of an electric drill that uses 9.45 amperes from a 120 volt source? Align the numbers to the right and multiply. After multiplying the numbers, count the total number of decimal places in both numbers. For this example, 9.45 has 2 decimal places, and 120 has no decimal place. Together there are 2 decimal places. The decimal point for the answer is placed 2 decimal places from the right. Therefore, the answer is 1134.00 watts, or simplified to 1134 watts. 9.45 times 120. 2 decimal places, no decimal place. 1890 plus 945. 1134.002 decimal places. Division of decimal numbers. Division of decimal numbers is performed the same way as whole numbers, unless the divisor is a decimal. Quotient, divisor, dividend. When the divisor is a decimal, it must be changed to a whole number before dividing. To do this, move the decimal in the divisor to the right until there are no decimal places. At the same time, move the decimal point in the dividend to the right the same number of places. Then divide. The decimal in the quotient is placed directly above the decimal in the dividend. Example. Divide 0.144 by 0.12. 1.2, 0.12, 0.144 equals 12. 14.4-12. 24-24. 0. Move the decimal in the divisor, 0.12, 2 places to the right. The result is 12.0. Next, move the decimal in the dividend, 0.144, 2 places to the right. The result is 14.4. Now divide. The result is 1.2. Example. The wing area of an airplane is 262.6 square feet, and its span is 40.4 feet. Find the mean chord of its wing using the formula, area divided by span equals mean chord. 3-6. 6.5, 40.4. 262.6 equals 404. 2626.0-2424. 2020 to 2020. 0. Move the decimal in the divisor, 40.4. 1 place to the right. Next, move the decimal in the dividend, 262.6, 1 place to the right. Then divide. The mean chord length is 6.5 feet. Rounding off decimal numbers. Occasionally, it is necessary to round off a decimal number to some value that is practical to use. For example, a measurement is calculated to be 29.4948 inches. To use this measurement, we can use the process of rounding off. A decimal is rounded off by keeping the digits for a certain number of places and discarding the rest. The degree of accuracy desired determines the number of digits to be retained. When the digit immediately to the right of the last retained digit is 5 or greater, round up by 1. When the digit immediately to the right of the last retained digit is less than 5, Leave the last retained digit unchanged. Example. An actuator shaft is 2.1938 inches in diameter. Round to the nearest tenth. The digit in the tenths column is a 1. The digit to the right of the 1 is a 9. Since 9 is greater than or equal to 5, round up the 1 to a 2. Therefore, 2.1938 rounded to the nearest tenth is 2.2. Example. The outside diameter of a bearing is 3.1648 centimeters. Round to the nearest hundredth. The digit in the hundredths column is a 6. The digit to the right of the 6 is a 4. Since 4 is less than 5, do not round up the 6. Therefore, 3.1648 to the nearest hundredth is 3.16. Example. The length of a bushing is 3.7487 feet. Round to the nearest thousandth. The digit in the thousandths column is an 8. The digit to the right of the 8 is a 7. Since 7 is greater than or equal to 5, round up the 8 to a 9. Therefore, 3.7487 to the nearest thousandth is 3.749. Converting decimal numbers to fractions. To change a decimal number to a fraction, read the decimal out loud, and then write it into a fraction just as it is. Read as shown below. Example. One oversized rivet has a diameter of 0.52 inches. Convert 0.52 to a fraction. The decimal 0.52 is read as 52 hundredths. 52. 0.52 equals 100 hundredths. In the above fraction of 52 hundredths, we can divide 4 into each number, resulting in a fraction of 13/25. A dimension often appears in a maintenance manual or on a blueprint as a decimal instead of a fraction. To use the dimension, it may need to be converted to a fraction. An aviation mechanic frequently uses a steel rule that is calibrated in units of 1/64 of an inch. To change a decimal to the nearest equivalent common fraction, multiply the decimal by 64. The product of the decimal and 64 is the numerator of the fraction, and 64 is the denominator. Reduce the fraction, if needed. Example. The width of a hex head bolt is 0.3123 inches. Convert the decimal 0.3123 to a common fraction to decide which socket would be the best fit for the bolt head. First, multiply the 0.3123 decimal by 64. 0.3123 times 64 equals 19.9872. Next, round the product to the nearest whole number, 19.9872 to almost equal to 20. Use this whole number, 20, as the numerator, and 64 as the denominator. 20/64. Now, reduce 20/64 to 5/16 as 4 is common to both the numerator and denominator. Therefore, the correct socket would be the 5/16 inch socket, 20/64 reduced. Example. When accurate holes of uniform diameter are required for aircraft structures, they are first drilled approximately 1/64 inch undersized, and then reamed to the final desired diameter. What size drill bit should be selected for the undersized hole, if the final hole is reamed to a diameter of 0.763 inches? First, multiply the 0.763 decimal by 64. 0.763 times 64 equals 48.832. Next, round the product to the nearest whole number, 48.832 almost equal to 49. Use this number, 49, as the numerator, and 64 as the denominator. 49/64 is the closest fraction to the final reaming diameter of 0.763 inches. To determine the drill size for the initial undersized hole, subtract 1/64 inch from the finished hole size. 3-7. 3. 8. Therefore, 49, 148 minus equals 64. 64. 64. 4. Therefore, a 3/4 inch drill bit should be used for the initial undersized holes. Converting fractions to decimals. To convert any fraction to a decimal, simply divide the top number, numerator, by the bottom number, denominator. Every fraction has an approximate decimal equivalent. Example. 0. 1.0 therefore, equals 0.5. 511 equals 1 divided by 2 equals 2. 2-1.0. 0. 0.375. Equals 3 divided by 8 equals 8. 3.000. Minus 24. 3. 8. Equals 0.375. 60-56. 40-40. 0. Calculator tip. Numerator. Top number divided by denominator. Bottom number equals the decimal equivalent of the fraction. Some fractions when converted to decimals produce a repeating decimal. Example. 0.33. 1. 3. Equals 1 divided by 3 equals 3. 1.00. Minus 9. Equals 0.3 or 0.33. This decimal can be 10 represented with a bar, or can minus 9 be rounded. A bar indicates 1. That the numbers beneath it are repeated to infinity. Other examples of repeating decimals. 0.212121 equals 0.21. 0.6666 equals 0.7 or 0.67. 0.254254 equals 0.254. Decimal equivalent chart. Figure 3-6 is a fraction to decimal to millimeter equivalency chart. Measurements starting at 1/64 inch and up to 23 inches have been converted to decimal numbers and to millimeters. Ratio. A ratio is the comparison of two numbers or quantities. A ratio may be expressed in three ways, as a fraction, with a colon, or with the word to. For example, a gear ratio of 5:7 can be expressed as any of the following: 5/7 or 5:7 or 5:7. Aviation applications. Ratios have widespread application in the field of aviation. Example: compression ratio on a reciprocating engine is the ratio of the volume of a cylinder with the piston at the bottom of its stroke to the volume of the cylinder with the piston at the top of its stroke. For example, a typical compression ratio might be 10:1 or 10:1. Aspect ratio is the ratio of the length or span of an airfoil to its width or chord. A typical aspect ratio for a commercial airliner might be 7:1 or 7:1. Air-fuel ratio is the ratio of the weight of the air to the weight of fuel in the mixture being fed into the cylinders of a reciprocating engine. For example, a typical air-fuel ratio might be 14.31 or 14.3:1. Glide ratio is the ratio of the forward distance traveled to the vertical distance descended when an aircraft is operating without power. For example, if an aircraft descends 1,000 feet, while it travels through the air for 2 linear miles, 10,560 feet, it has a glide ratio of 10,560, 1,000, which can be reduced to 10.561, or 10.56:1. Gear ratio is the number of teeth each gear represents when 2 gears are used in an aircraft component. In figure 3-7, the pinion gear has 8 teeth and a spur gear has 28 teeth. The gear ratio is 8:28. Using 7 as the LCD, 8:28 becomes 2:7. Speed ratio is when 2 gears are used in an aircraft component. The rotational speed of each gear is represented as a speed ratio. As the number of teeth in a gear decreases, the rotational speed of that gear increases, and vice versa. Therefore, the speed ratio of 2 gears is the inverse, or opposite, of the gear ratio. If 2 gears have a gear ratio of 2:9, then their speed ratio is 9:2. Example: a pinion gear with 10 teeth is driving a spur gear with 40 teeth. The spur gear is rotating at 160 rpm. Calculate the speed of the pinion gear. Teeth in pinion gear speed of spur gear equals teeth in spur gear speed of pinion gear. 3-8. Fraction decimal mm. 1/64th 0.015, 0.396. 1/32nd 0.031, 0.793. 3/64ths 0.046, 1.190. 1/16th 0.062, 1.587. 5/64ths 0.078, 1.984. 3/32nds 0.093, 2.381. 7/64ths 0.109, 2.778. 1/8th 0.125, 3.175. 9/64ths 0.140, 3.571. 5/32nds 0.156, 3.968. 11/64ths 0.171, 4.365. 3/16ths 0.187, 4.762. 13/64ths 0.203, 5.159. 7/32nds 0.218, 5.556. 15/64ths 0.234, 5.953. 1/4 0.25, 6.35. 17/64ths 0.265, 6.746. 9/32nds 0.281, 7.143. 19/64ths 0.296, 7.540. 5/16ths 0.312, 7.937. 21/64ths 0.328, 8.334. 11/32nds 0.343, 8.731. 23/64ths 0.359, 9.128. 3/8ths 0.375, 9.525. 25/64ths 0.390, 9.921. 13/32nds 0.406, 10.318. 27/64ths 0.421, 10.715. 7/16ths 0.437, 11.112. 29/64ths 0.453, 11.509. 15/32nds 0.468, 11.906. 31/64ths 0.484, 12.303. 1/2 0.5, 12.7. 33/64ths 0.515, 13.096. 17/32nds 0.531, 13.493. 35/64ths 0.546, 13.890. 39,341, 0.562, 14.287. 37/64ths 0.578, 14.684. 19/32nds 0.593, 15.081. 39/64ths 0.609, 15.478. 5/8ths 0.625, 15.875. 41/64ths 0.640, 16.271. 21/32nds 0.656, 16.668. 43/64ths 0.671, 17.065. 11 sixteenths 0.687, 17.462. 45 64ths 0.703, 17.859. 23 30seconds 0.718, 18.256. 47 64ths 0.734, 18.653. 3/4 0.75, 19.05. 49 64ths 0.765, 19.446. 25 30seconds 0.781, 19.843. 51 64ths 0.796, 20.240. 13 sixteenths 0.812, 20.637. 53 64ths 0.828, 21.034. 27 30seconds 0.843, 21.431. 55 64ths 0.859, 21.828. 7 eighths 0.875, 22.225. 57 64ths 0.890, 22.621. 29 30seconds 0.906, 23.018. 59 64ths 0.921, 23.415. 15 sixteenths 0.937, 23.812. 61 64ths 0.953, 24.209. 31 30seconds 0.968, 24.606. 63 64ths 0.984, 25.003. 1, 1, 25.4. Figure 3-6. Fractions, decimals, and millimeters. Fraction decimal mm. 1 and 1/64th 1.015, 25.796. 1 and 1/32nd 1.031, 26.193. 1 and 3/64ths 1.046, 26.590. 1 and 1/16th 1.062, 26.987. 1 and 5/64ths 1.078, 27.384. 1 and 3/32 1.093, 27.781. 1 and 7/64ths 1.109, 28.178. 1 and 1/8 1.125, 28.575. 1 and 9/64ths 1.140, 28.971. 1 and 5/32 1.156, 29.368. 1 and 11/64ths 1.171, 29.765. 1 and 3/16ths 1.187, 30.162. 1 and 13/64ths 1.203, 30.559. 1 and 7/32 1.218, 30.956. 1 and 15/64ths 1.234, 31.353. 1 and 1/4 1.25, 31.75. 1 and 17/64ths 1.265, 32.146. 1 and 9/32 1.281, 32.543. 1 and 19/64ths 1.296, 32.940. 1 and 5/16ths 1.312, 33.337. 1 and 21/64ths 1.328, 33.734. 1 and 11/32 1.343, 34.131. 1 and 23/64ths 1.359, 34.528. 1 and 3/8ths 1.375, 34.925. 1 and 25/64ths 1.390, 35.321. 1 and 13/32 1.406, 35.718. 1 and 27/64ths 1.421, 36.115. 1 and 7/16ths 1.437, 36.512. 1 and 29/64ths 1.453, 36.909. 1 and 15/32 1.468, 37.306. 1 and 31/64ths 1.484, 37.703. 1 and 1/2 1.5, 38.1. 1 and 33/64ths 1.515, 38.496. 1 and 17/32 1.531, 38.893. 1 and 35/64ths 1.546, 39.290. 1 and 9/16ths 1.562, 39.687. 1 and 37/64ths 1.578, 40.084. 1 and 19/32 1.593, 40.481. 1 and 39/64ths 1.609, 40.878. 1 and 5/8ths 1.625, 41.275. 1 and 41/64ths 1.640, 41.671. 1 and 21/32 1.656, 42.068. 1 and 43/64ths 1.671, 42.465. 1 and 11/16ths 1.687, 42.862. 1 and 45/64ths 1.703, 43.259. 1 and 23/32 1.718, 43.656. 1 and 47/64ths 1.734, 44.053. 1 and 3/4 1.75, 44.45. 1 and 49/64 1.765, 44.846. 1 and 25/32 1.781, 45.243. 1 and 51/64 1.796, 45.640. 1 and 13/16 1.812, 46.037. 1 and 53/64 1.828, 46.434. 1 and 27/32 1.843, 46.831. 1 and 55/64 1.859, 47.228. 1 and 7/8 1.875, 47.625. 1 and 57/64 1.890, 48.021. 1 and 29/32 1.906, 48.418. 1 and 59/64 1.921, 48.815. 1 and 15/16 1.937, 49.212. 1 and 61/64 1.953, 49.609. 1 and 31/32 1.968, 50.006. 1 and 63/64 1.984, 50.403. 2, 50.8. Fraction decimal mm. 2 and 1/64 2.015, 51.196. 2 and 1/32 2.031, 51.593. 2 and 3/64 2.046, 51.990. 2 and 1/16 2.062, 52.387. 2 and 5/64 2.078, 52.784. 2 and 3/32 2.093, 53.181. 2 and 7/64 2.109, 53.578. 2 and 1/8 2.125, 53.975. 2 and 9/64 2.140, 54.371. 2 and 5/32 2.156, 54.768. 2 and 11/64 2.171, 55.165. 2 and 3/16 2.187, 55.562. 2 and 13/64 2.203, 55.959. 2 and 7/32 2.218, 56.356. 2 and 15/64 2.234, 56.753. 2 and 1/4 2.25, 57.15. 2 and 17/64 2.265, 57.546. 2 and 9/32 2.281, 57.943. 2 and 19/64 2.296, 58.340. 2 and 5/16 2.312, 58.737. 2 and 21/64 2.328, 59.134. 2 and 11/32 2.343, 59.531. 2 and 23/64 2.359, 59.928. 2 and 3/8 2.375, 60.325. 2 and 25/64 2.390, 60.721. 2 and 13/32 2.406, 61.118. 2 and 27/64 2.421, 61.515. 2 and 7/16 2.437, 61.912. 2 and 29/64 2.453, 62.309. 2 and 15/32 2.468, 62.706. 2 and 31/64 2.484, 63.103. 2 and 1/2 2.5, 63.5. 2 and 33/64 2.515, 63.896. 2 and 17/32 2.531, 64.293. 2 and 35/64 2.546, 64.690. 2 and 9/16 2.562, 65.087. 2 and 37/64 2.578, 65.484. 2 and 19/32 2.593, 65.881. 2 and 39/64 2.609, 66.278. 2 and 5/8 2.625, 66.675. 2 and 41/64 2.640, 67.071. 2 and 21/32 2.656, 67.468. 2 and 43/64 2.671, 67.865. 2 and 11/16 2.687, 68.262. 2 and 45/64 2.703, 68.659. 2 and 23/32 2.718, 69.056. 2 and 47/64 2.734, 69.453. 2 and 3/4 2.75, 69.85. 2 and 49/64 2.765, 70.246. 2 and 25/32 2.781, 70.643. 2 and 51/64 2.796, 71.040. 2 and 13/16 2.812, 71.437. 2 and 53/64 2.828, 71.834. 2 and 27 30seconds 2.843, 72.231. 2 and 55 64ths 2.859, 72.628. 2 and 7/8ths 2.875, 73.025. 2 and 57 64ths 2.890, 73.421. 2 and 29 30seconds 2.906, 73.818. 2 and 59 64ths 2.921, 74.215. 2 and 15 16ths 2.937, 74.612. 2 and 61 64ths 2.953, 75.009. 2 and 31 30seconds 2.968, 75.406. 2 and 63 64ths 2.984, 75.803. 3, 76.2. 3-9. 2, 7. Figure 3-7. Gear ratio. 10th 160 rpm equals 40th sp. Speed of pinion gear. To solve for sp, multiply 40 times 160, then divide by 10. The speed of the pinion gear is 640 rpm. Example. If the cruising speed of an airplane is 200 knots, and its maximum speed is 250 knots, what is the ratio of cruising speed to maximum speed? First, express the cruising speed as the numerator of a fraction whose denominator is the maximum speed. 200 ratio equals 250. Next, reduce the resulting fraction to its simplest form. 204 ratio equals 250, 5. Therefore, the ratio of cruising speed to maximum speed is 4. 5. Another common use of ratios is to convert any given ratio to an equivalent ratio with a denominator of 1. Example. Express the ratio 9, 5 as a ratio with a denominator of 1. 9, 1.8. R equals since 9 divided by 5 equals 1.8, then equals 5, 1, 5, 1. Therefore, 9, 5 is the same ratio as 1.8, 1. In other words, 9 to 5 is the same ratio as 1.8 to 1. Proportion. A proportion is a statement of equality between two or more ratios. For example, 3, 6 equals or 3, 4 equals 6. 8, 4, 8. This proportion is read as 3 is to 4 as 6 is to 8. Extremes and means. The first and last terms of the proportion, the 3 and 8 in this example, are called the extremes. The second and third terms, the 4 and 6 in this example, are called the means. In any proportion, the product of the extremes is equal to the product of the means. In the proportion 2, 3 equals 4. 6. The product of the extremes, 2 times 6, is 12. The product of the means, 3 times 4, is also 12. An inspection of any proportion shows this to be true. Solving proportions. Normally when solving a proportion, 3 quantities are known, and the fourth is unknown. To solve for the unknown, multiply the two numbers along the diagonal, and then divide by the third number. Example. Solve for x in the proportion given below. 65x equals 80,100. First, multiply 65 times 100. 65 times 100 equals 6,500. Next, divide by 80. 6,500 divided by 80 equals 81.25. Therefore, x equals 81.25. Example. An airplane flying 300 miles used 24 gallons of gasoline. How many gallons will it need to travel 750 miles? The ratio here is miles to gallons. Therefore, the proportion is set up as miles 300 equals 750 gallons 24 g. Solve for g. 750 times 24 divided by 300 equals 60. Therefore, to fly 750 miles, 60 gallons of gasoline is required. Percentage. Percentage means parts out of 100. The percentage sign is percent. 90% is expressed as 90% equals 90 parts out of 100. The decimal 0.90 equals 90 hundredths, or 90 out of 100, or 90%. Expressing a decimal number as a percentage. To express a decimal number in percent, move the decimal point 2 places to the right, adding zeros if necessary, and then affix the percent symbol. Example. Express the following decimal numbers as a percent. 0.90 equals 90%, 0.5 equals 50%. 3-10. 1.25 equals 125%, 0.335 equals 33.5%. Expressing a percentage as a decimal number. Sometimes it may be necessary to express a percentage as a decimal number. To express a percentage as a decimal number, move the decimal point 2 places to the left, and drop the percent symbol. For example, express the following percentages as decimal numbers. 90% equals 0.90. 50% equals 0.50. 5% equals 0.05. 150% equals 1.5. Expressing a fraction as a percentage. To express a fraction as a percentage, first change the fraction to a decimal number by dividing the numerator by the denominator, and then convert the decimal number to a percentage by multiplying by 100 as shown earlier. Example. Express the fraction 5/8 as a percentage. 5 equals 5 divided by 8 equals 0.625 equals 62.5%. 8. Finding a percentage of a given number. This is the most common type of percentage calculation. Here are two methods to solve percentage problems, using algebra or using proportions. Each method is shown next to find a percent of a given number. Example. In a shipment of 80 wingtip lights, 15% of the lights were defective. How many of the lights were defective? Algebraic method. 15% of 80 lights equals n, number of defective lights. 0.15 times 80 equals n, 12 equals n. Therefore, 12 defective lights were in the shipment. Proportion method. N15 equals 80,100. To solve for n times 100 equals 80 times 15. N times 100 equals 1,200. N equals 1,200 divided by 100. N equals 12. Or n equals 80 times 15 divided by 100. N equals 12. Finding what percentage one number is of another. Example. A small engine rated at 12 horsepower is found to be delivering only 10.75 horsepower. What is the motor efficiency expressed as a percent? Algebraic method. N% of 12 rated horsepower equals 10.75 actual horsepower. N% times 12 equals 10.75. N% equals 10.75 divided by 12. N% equals 0.8958. N equals 89.58. Therefore, the motor efficiency is 89.58%. Proportion method. 10.75 n equals 12,100. To solve for n times 12 equals 10.75 times 100. N times 12 equals 1,075. N equals 1,075 divided by 12. N equals 89.58 or n equals 1,075 times 100 divided by 12. N equals 89.58. Therefore, the motor efficiency is 89.58%. Finding a number when a percentage of it is known. Example. 80 ohms represents 52% of a microphone's total resistance. Find the total resistance of this microphone. Algebraic method. 52% of n equals 80 ohms. 52% times n equals 80. N equals 80 divided by 0.52. N equals 153.846. The total resistance of the microphone is 153.846 ohms. Proportion method. 80. 52 equals n 100. To solve for n times 52 equals 80 times 100. N times 52 equals 8,000. N equals 8,000 divided by 52. N equals 153.846 ohms or n equals 80 times 100 divided by 52. N equals 153.846 ohms. 3-11. Positive and negative numbers. Signed numbers. Positive numbers are numbers that are greater than 0. Negative numbers are numbers less than 0. Figure 3-8. Signed numbers are also called integers. Addition of positive and negative numbers. The sum, addition, of two positive numbers is positive. The sum, addition, of two negative numbers is negative. The sum of a positive and a negative number can be positive or negative, depending on the values of the numbers. A good way to visualize a negative number is to think in terms of debt. If you are in debt by $100, or minus 100, and you add $45 to your account, you are now only $55 in debt, or minus 55. Therefore, minus 100 plus 45 equals minus 55. Example. The weight of an aircraft is 2,000 pounds. A radio rack weighing 3 pounds and a transceiver weighing 10 pounds are removed from the aircraft. What is the new weight? For weight and balance purposes, all weight removed from an aircraft is given a minus sign, and all weight added is given a plus sign. 2,000 plus minus 3 plus minus 10 equals 2,000 plus minus 13 equals 1,987. Therefore, the new weight is 1,987 pounds. Subtraction of positive and negative numbers. To subtract positive and negative numbers, first change the dash subtraction symbol to a plus addition symbol, and change the sign of the second number to its opposite. That is, change a positive number to a negative number or vice versa. Finally, add the two numbers together. Example. The daytime temperature in the city of Denver was 6 degrees below 0-6 degrees. An airplane is cruising at 15,000 feet above Denver. The temperature at 15,000 feet is 20 degrees colder than in the city of Denver. What is the temperature at 15,000 feet? Subtract 20 from minus 6. Minus 6 minus 20 equals minus 6 plus minus 20 equals minus 26. The temperature is minus 26 degrees, or 26 degrees below 0 at 15,000 feet above the city. Minus 5-4-3-2-1 plus 1 plus 2 plus 3 plus 4 plus 5. Multiplication of positive and negative numbers. The product of two positive numbers is always positive. The product of two negative numbers is always positive. The product of a positive and a negative number is always negative. Examples. 3 times 6 equals 18 minus 3 times 6 equals minus 18 minus 3 times minus 6 equals 18 3 times minus 6 equals minus 18. Division of positive and negative numbers. The quotient of two positive numbers is always positive. The quotient of two negative numbers is always positive. The quotient of a positive and negative number is always negative. Examples. 6 divided by 3 equals 2 minus 6 divided by 3 equals minus 2 minus 6 divided by minus 3 equals 2 6 divided by minus 3 equals minus 2. Powers. The power, or exponent, of a number is a shorthand method of indicating how many times a number, called the base, is multiplied by itself. For example, 3/4 is read as 3 to the power of 4. That is, 3 multiplied by itself 4 times. The 3 is the base and 4 is the power. Examples: 2 3 equals 2 times 2 times 2 equals 8. Read 2 to the third power equals 8. 10 5 equals 10 times 10 times 10 times 10 times 10 equals 100,000. Read 10 to the fifth power equals 100,000. Special powers. Squared. When a number has a power of 2, it is commonly referred to as squared. For example, 7/2 is read as 7 squared, or 7 to the second power. To remember this, think about how a square has 2 dimensions, length and width, cubed. When a number has a power of 3, it is commonly referred to as cubed. For example, 7/3 is read as 7 cubed, or 7 to the third power. To remember this, think about how a cube has 3 dimensions, length, width, and depth. Power of 0. Any non-zero number raised to the 0 power always equals 1. Example: 7, 0 equals 1, 181, 0 equals 1, minus 24, 0 equals 1. Figure 3-8. A scale of signed numbers. 3-12. Negative powers. A number with a negative power equals its reciprocal with the same power made positive. Example: the number 2-3 is read as 2 to the negative third power, and is calculated by 1. 1 1 2 minus 3 equals 2. 3 2 times 2 times 2, 8. When using a calculator to raise a negative number to a power, always place parentheses around the negative number before raising it to a power, so that the entire number gets raised to the power. Law of exponents. When multiplying numbers with powers, the powers can be added as long as the bases are the same. Example: 3, 2 times 3, 4 equals 3 times 3 times 3 times 3 times 3 times 3 equals 3 times 3 times 3 times 3 times 3 times 3 equals 3, 6. Or 3, 2 times 3, 4 equals 3, 2 plus 4 equals 3, 6. When dividing numbers with powers, the powers can be subtracted as long as the bases are the same. Example: 10 times 10 times 10 times 10 10 times 10 times 10 times 10. 10. 4 divided by 10 2 equals 10 times 10 equals 10, 2. 10 times 10, 10 times 10. Or 10. 4 divided by 10, 2 equals 10, 4 minus 2 equals 10, 2. Powers of 10. Because we use the decimal system of numbers, powers of 10 are frequently seen in everyday applications. For example, scientific notation uses powers of 10. Also, many aircraft drawings are scaled to powers of 10. Figure 3-9 gives more information on the powers of 10 and their values. Roots. A root is a number that when multiplied by itself a specified number of times produces a given number. The two most common roots are the square root and the cube root. For more examples of roots, see figure 3-10. Square roots. The square root of 25, written as 25, equals 5. That is, when the number 5 is squared, multiplied by itself, it produces the number 25. The symbol is called a radical sign. Finding the square root of a number is the most common application of roots. The collections of numbers, whose square roots are whole numbers, are called perfect squares. The first 10 perfect squares are 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. Powers of 10. Expansion value. Positive exponents. 10, 6 10x 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 10, 1,010,000, 5 10x 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 10,100, 000 10, 4 10x 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 10, 10,010, 3 10x 10x 10, 1,010, 2, 10x 10, 100, 10, 1, 10, 10, 10, 0, 1 negative exponents. 10 minus 1 and 1/10 1 divided by 10 equals 0.1. 10 minus 2, 1 divided by 10x 10, 1 divided by 100 equals 0.01. 10-3, 1/10x 10x 10, 1/1000 equals 0.001. 10-4, 1/10x 10x 10x 10, 1/10,000 equals 0.0001. 10-5, 1/10x 10x 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 10, 1/100,000 equals 0.00001. 10-6, 1/10x 10x 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 10, 1/1,000,000 equals 0.00001. Figure 3-9. Powers of 10. The square root of each of these numbers is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, respectively. For example, 36 equals 6 and 81 equals 9. To find the square root of a number that is not a perfect square, use either a calculator or the estimation method. A longhand method does exist for finding square roots, but with the advent of calculators, and because of its lengthy explanation, it is no longer included in this handbook. The estimation method uses the knowledge of perfect squares to approximate the square root of a number. Example. Find the square root of 31. Since 31 falls between the two perfect roots 25 and 36, we know that must be between 25 and 36. Therefore, 31 must be greater than 5, and less than 6 because 25 equals 5 and 36 equals 6. If you estimate the square root of 31 at 5.5, you are close to the correct answer. The square root of 31 is actually 5.568 cube roots. The cube root of 125, written as 3125, equals 5. That is, when the number 5 is cubed, 5 multiplied by itself then multiplying the product, 25, by 5 again, it produces the number 125. It is common to confuse the cube of a number with the cube root of a number. For clarification, the cube of 27 equals 27. 3 equals 27 times 27 times 27 equals 19,683. However, the cube root of 27 equals 3. 27 equals 3. 3-13. Number square root cube root circumference area. Number n squared, n2, n cubed, n3, square root cube root. 3. Circumference of a circle with 5, 10, 15, 20. Area of a circle with of n, square root n, of n, square root n, diameter equals n, diameter equals n. 1, 1, 1, 1.000, 1.000, 3.142, 0.785. 2, 4, 8, 1.414, 1.260, 6.283, 3.142. 3, 9, 27, 1.732, 1.442, 9.425, 7.069. 4, 16, 64, 2.000, 1.587, 12.566, 12.566. 25, 125, 2.236, 1.710, 15.708, 19.635. 6, 36, 216, 2.449, 1.817, 18.850, 28.274. 7, 49, 343, 2.646, 1.913, 21.991, 38.484. 8, 64, 512, 2.828, 2.000, 25.133, 50.265. 9, 81, 729, 3.000, 2.080, 28.274, 63.617. 100, 1000, 3.162, 2.154, 31.416, 78.540. 11, 121, 1331, 3.317, 2.224, 34.558, 95.033. 12, 144, 1728, 3.464, 2.289, 37, 699, 113. 01, 13, 169, 2197, 3.606, 2.351, 40, 841, 132. 73, 14, 196, 2744, 3.742, 2.410, 43, 982, 153. 94, 225, 3375, 3.873, 2.466, 47, 124, 176. 71, 16, 256, 4096, 4.000, 2.520, 50265, 201. 06, 17, 289, 4913, 4.123, 2.571, 53, 407, 226. 98, 18, 324, 5832, 4.243, 2.621, 56, 549, 254. 47, 19, 361, 6859, 4.359, 2.668, 59, 690, 283. 53, 400, 8000, 4.472, 2.714, 62, 832, 314. 16, 21, 441, 9261, 4.583, 2.759, 65, 973, 346. 36, 22, 484, 10,648, 4.690, 2.802, 69, 115, 380. 13, 23, 529, 12,167, 4.796, 2.844, 72, 257, 415. 48, 24, 576, 13,824, 4.899, 2.885, 75, 398, 452. 39, 625, 15,625, 5.000, 2.924, 78, 540, 490. 87, 26, 676, 17,576. 5.099, 2.963, 81, 681, 530. 93. 27. 729, 19,683, 5.196, 3.000, 84, 823, 572. 55. 28. 784, 21,952, 5.292, 3.037, 87, 965, 615. 75. 29, 841, 24,389, 5.385, 3.072, 91, 106, 660. 52. 900, 27,000, 5.477, 3.107, 94, 248, 706. 86. 31. 961, 29,791, 5.568, 3.141, 97, 389, 754. 77. 32. 1,024, 32,768, 5.657, 3, 175, 100. 531,804.25. 33. 1,089, 35,937, 5.745, 3, 28, 103. 672,855.30. 34. 1,156, 39,304, 5.831, 3, 240, 106. 814,907.92. 1,225, 42,875, 5.916, 3, 271, 109. 956,962.11. 36. 1,296, 46,656, 6.000, 3, 302, 113. 097, 1017. 88. 37. 1,369, 50,653, 6.083, 3, 332, 116. 239, 1075. 21. 38. 1,444, 54,872, 6.164, 3, 362, 119. 380, 1134. 11. 39, 1,521, 59,319, 6.245, 3, 391, 122. 522, 1194. 59. 1,600, 64,000, 6.325, 3, 420, 125. 664, 1256. 64. 41. 1,681, 68,921, 6.403, 3, 448, 128. 805, 1320. 25. 42. 1,764, 74,088, 6.481, 3, 476, 131. 947, 1385. 44. 43. 1,849, 79,507, 6.557, 3, 503, 135. 088, 1452. 20. 44. 1,936, 85,184, 6.633, 3, 530, 138. 230, 1520. 53. 2,025, 91,125, 6.708, 3, 557, 141. 372, 1590. 43. 46. 2,116, 97,336, 6.782, 3, 583, 144. 513, 1661. 90. 47. 2,209, 103,823, 6.856, 3, 609, 147. 655, 1734. 94. 48. 2,304, 110,592, 6.928, 3, 634, 150. 796, 1809. 56. 49. 2,401, 117,649, 7.000, 3, 659, 153. 938, 1885. 74. 2,500, 125,000, 7.071, 3, 684, 157. 080, 1963. 49. 25. 30. 35. 40. 45. 50. Figure 3-10. Functions of numbers. 3-14. Number square root circumference area. Number n squared, n2, n cubed, n3, square root cube root. 3. Circumference of a circle with area of circle width of n, square root n, of n, square root n, diameter equals n, diameter equals n. 51, 2601, 132,651, 7.141, 3, 708, 160. 221, 2042. 82, 52, 2704, 140,608, 7.211, 3, 733, 163. 363, 2123. 71. 53, 2809, 148,877, 7.280, 3, 756, 166. 504, 2206. 18. 54, 2916, 157,464, 7.348, 3, 780, 169. 646, 2290. 22. 55, 3025, 166,375, 7.416, 3, 803, 172. 787, 2375. 83, 56, 3136, 175,616, 7.483, 3, 826, 175. 929, 2463. 01, 57, 3,249, 185,193, 7.550, 3, 849, 179. 071, 2551. 76. 58, 3,364, 195,112, 7.616, 3, 871, 182. 212, 2642. 08. 59, 3,481, 205,379, 7.681, 3, 893, 185. 354, 2733. 97. 60, 3,600, 216,000, 7.746, 3, 915, 188. 495, 2827. 43. 61, 3,721, 226,981, 7.810, 3, 937, 191. 637, 2922. 46. 62, 3,844, 238,328, 7.874, 3, 958, 194. 779, 3109. 07. 63, 3,969, 250,047, 7.937, 3, 979, 197. 920, 3117. 24. 64, 4,096, 262,144, 8.000, 4, 000, 201. 062, 3216. 99. 65, 4,225, 274,625, 8.062, 4, 021, 204. 203, 3318. 30. 66, 4,356, 287,496, 8.124, 4, 041, 207. 345, 3421. 19. 67, 4,489, 300,763, 8.185, 4, 062, 210. 487, 3525. 65. 68, 4,624, 314,432, 8.246, 4, 082, 213. 628, 3631. 68. 69, 4,761, 328,509, 8.307, 4, 102, 216. 770, 3739. 28. 70, 4,900, 343,000, 8.367, 4, 121, 219. 911, 3848. 45. 71, 5,041, 357,911, 8.426, 4, 141, 223. 053, 3959. 19. 72, 5,184, 373,248, 8.485, 4, 160, 226. 194, 4071. 50. 73, 5,329, 389,017, 8.544, 4, 179, 229. 336, 4185. 38. 74, 5,476, 405,224, 8.602, 4, 198, 232. 478, 4300. 84. 75. 5625. 421,875. 8.660. 4. 217. 235. 619. 4417. 86. 76. 5776. 438,976. 8.718. 4. 236. 238. 761. 4536. 46. 77. 5,929. 456,533. 8.775. 4. 254. 241. 902. 4656. 62. 78. 6,084. 474,552. 8.832. 4. 273. 245. 044. 4778. 36. 79. 6,241. 493,039. 8.888. 4. 291. 248. 186. 4901. 67. 80. 6,400. 512,000. 8.944. 4. 309. 251. 327. 5026. 54. 81. 6,561. 531,441. 9.000. 4. 327. 254. 469. 5152. 99. 82. 6,724. 551,368. 9.055. 4. 344. 257. 610. 5281. 01. 83. 6,889. 571,787. 9.110. 4. 362. 260. 752. 5410. 60. 84. 7,056. 592,704. 9.165. 4. 380,263. 894. 5541. 76. 85. 7,225. 614,125. 9.220. 4. 397. 267. 035. 5674. 50. 86. 7,396. 636,056. 9.274. 4. 414. 270. 177. 5808. 80. 87. 7,569. 658,503. 9.327. 4. 431. 273. 318. 5944. 67. 88. 7,744. 681,472. 9.381. 4. 448. 276. 460. 6082. 12. 89. 7,921. 704,969. 9.434. 4. 465. 279. 602. 6221. 13. 90. 8,100. 729,000. 9.487. 4. 481. 282. 743. 6361. 72. 91. 8,281. 753,571. 9.539. 4. 498. 285. 885. 6503. 88. 92. 8,464. 778,688. 9.592. 4. 514. 289. 026. 6647. 60. 93. 8,649. 804,357. 9.644. 4. 531. 292. 168. 6792. 90. 94. 8,836. 830,584. 9.695. 4. 547. 295. 309. 6939. 77. 95. 9,025. 857,375. 9.747. 4. 563. 298. 451. 7088. 21. 96. 9,216. 884,736. 9.798. 4. 579. 301. 593. 7238. 22. 97. 9,409. 912,673. 9.849. 4. 595. 304. 734. 7389. 81. 98. 9,604. 941,192. 9.900. 4. 610-307. 876-7542. 96. 99, 9801, 970,299, 9.950, 4, 626, 311. 017, 7697. 68. 110,000, 1,000,000, 10.000, 4, 642, 314. 159, 7853. 98. Figure 3-10. Functions of numbers. Continued. 3-15. 1. 4. Fractional powers. Another way to write a root is to use a fraction as the power, or exponent, instead of the radical sign. The square root of a number is written with 1/2 as the exponent instead of a radical sign. The cube root of a number is written with an exponent of 1/3, and the fourth root with an exponent of 1/4 and so on. /2 3/3 4 example. 31 equals 31. 1125 equals 125. 1. 16 equals 16. Functions of numbers chart. The functions of numbers chart found in figure 3-10 is included in this chapter for convenience in making computations. Each column in the chart is listed below, with new concepts explained. Number n squared, n2, n cubed, n3, square root of n, cube root of n, 3n. Circumference of a circle with diameter equals n. Circumference is the linear measurement of the distance around a circle. The circumference is calculated by multiplying the diameter of the circle by 3.1416. 3.1416 is the number referred to as pi, which has the symbol pi. If the diameter of a circle is 10 inches, then the circumference would be 10 times 3.1416 equals 31.4160. Area of a circle with diameter equals n. Area of a circle is the number of square units of measurement contained in the circle with a diameter of n. The area of a circle equals pi multiplied by the radius squared. This is calculated by the formula a equals pi times r2. Remember that the radius is equal to 1/2 of the diameter. Example. A flight deck instrument gauge has a round face that is 3 inches in diameter. What is the area of the face of the gauge? From figure 3-10 for n equals 3, the answer is 7.0686 square inches. This is calculated by, if the diameter of the gauge is 3 inches, then the radius equals d divided by 2 equals 3 divided by 2 equals 1.5 inches. Area equals pi times r2 equals 3.1416 times 1.5, 2 equals 3.1416 times 2.25 equals 7.0686 square inches. Scientific notation. Scientific notation is used as a type of shorthand to express very large or very small numbers. It is a way to write numbers, so that they do not take up as much space on the page. The format of a number written in scientific notation has two parts. The first part is a number greater than or equal to 1 and less than 10, for example, 2.35. The second part is a power of 10, for example, 10, 6. The number 2,350,000 is expressed in scientific notation as 2.35 times 10, 6. It is important that the decimal point is always placed to the right of the first digit. Notice that very large numbers always have a positive power of 10, and very small numbers always have a negative power of 10. Example. The velocity of the speed of light is over 186,000 miles per second, MPS. This can be expressed as 1.86 times 10, 5 MPS in scientific notation. The mass of an electron is approximately 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 911 grams. This can be expressed in scientific notation as 9.11 times 10-28 grams. Converting numbers from standard notation to scientific notation. Example. Convert 1,244. 000,000,000 to scientific notation as follows. First, note that the decimal point is to the right of the last zero. Even though it is not usually written, it is assumed to be there. 1,244. 000,000,000 equals 1,244. 000,000,000.0. To change to the format of scientific notation, the decimal point must be moved to the position between the first and second digits. In this case, it is between the 1 and the 2. Since the decimal point must be moved 12 places to the left to get there, the power of 10 is 12. Remember that large numbers always have a positive exponent. Therefore, 1,244. 000,000,000 equals 1.244 times 10, 12 when written in scientific notation. Example. Convert 0.000000457 from standard notation to scientific notation. To change to the format of scientific notation, the decimal point must be moved to the position between the first and second numbers, which in this case is between the 4 and the 5. Since the decimal point must be moved 7 places to the right to get there, the power of 10 is minus 7. Remember that small numbers, those less than 1, have a negative exponent. Therefore, 0.000000457 equals 4.57 times 10-7 when written in scientific notation. Converting numbers from scientific notation to standard notation. Example. Convert 3.68 times 10, 7 from scientific notation to standard notation, as follows. To convert from scientific notation to standard notation, move the decimal place 7 places to the right. 3.68 times 10, 7 equals 36,800,000. Another way to think about the conversion is 3.68 times 10, 7 equals 3.68 times 10 million equals 36,800,000. Example. Convert 7.1543 times 10-10 from scientific notation to standard notation. Move the decimal place 10 places to the left. 7.1543 times 10 minus 10 equals. Group of zeros, 71543. Another way to think about the conversion is 7.1543 times 10 minus 10 equals 7.1543 times 0.00000000001 equals 0.000000000071543. 3-16. When converting, remember that large numbers always have positive powers of 10, and small numbers always have negative powers of 10. Refer to figure 3-11 to determine which direction to move the decimal point. Addition, subtraction, multiplication, and division of scientific numbers. To add, subtract, multiply, or divide numbers in scientific notation, change the scientific notation number back to standard notation. Then add, subtract, multiply or divide the standard notation numbers. After the computation, change the final standard notation number back to scientific notation. Algebra. Algebra is the branch of mathematics that uses letters or symbols to represent variables in formulas and equations. For example, in the equation d equals v times t, where distance equals velocity times time, the variables are d, v, and t. Equations. Algebraic equations are frequently used in aviation to show the relationship between two or more variables. Equations normally have an equals sign, equals, in the expression. Example. The formula, a equals pi times r2 shows the relationship between the area of a circle, a, and the length of the radius, r, of the circle. The area of a circle is equal to pi, 3.1416, times the radius squared. The larger the radius, the larger the area of the circle. Algebraic rules. When solving for a variable in an equation, you can add, subtract, multiply, or divide the terms in the equation. You do the same to both sides of the equals sign, to get the variable onto one side of the equals sign. Examples. Solve the following equations for the value n. 3n equals 21. To solve for n, divide both sides by 3. 3n divided by 3 equals 21 divided by 3n equals 7. n plus 17 equals 59. To solve for n, subtract 17 from both sides. n plus 17 minus 17 equals 59 minus 17 n equals 42. n minus 22 equals 100. To solve for n, add 22 to both sides. n minus 22 plus 22 equals 100 plus 22 n equals 122. n equals 50. 5. To solve for n, multiply both sides by 5. n times 5 equals 50 times 5. n equals 250. Solving for a variable. Another application of algebra is to solve an equation for a given variable. Example. Using the formula given in figure 3-12. Find the total capacitance, CT, of the series circuit containing 3 capacitors with C1 equals 0.1 microfarad, C2 equals 0.015 microfarad, C3 equals 0.05 microfarad. First, substitute the given values into the formula. 1 CT equals 1, 1, 1, 1, 1. 10 plus 66.66 plus 20 plus C1 C2 C3 0.1, 0.015, 0.05. Therefore, CT equals 1/96.66 equals 0.01034 microfarad. The microfarad, 10-6 farad, is a unit of measurement of capacitance. This is discussed in greater length in Chapter 12. Electricity. CT equals 1. C1. 1. Plus. 1. C2. Plus. 1. C3. Large numbers small numbers conversion with positive with negative powers of 10 powers of 10. Figure 3-12. Total capacitance in a series circuit. From standard notation to scientific notation. From scientific notation to standard notation. Move decimal place to the left. Move decimal place to the right. Move decimal place to the right. Move decimal place to the left. Figure 3-11. Converting between scientific and standard notation. 3-17. Use of parentheses. In algebraic equations, parentheses are used to group numbers or symbols together. The use of parentheses helps us to identify the order in which we should apply mathematical operations. The operations inside the parentheses are always performed first in algebraic equations. Example. Solve the algebraic equation x equals 4 plus 3, 2. First, perform the operation inside the parentheses, which is 4 plus 3 equals 7. Then complete the exponent calculation x equals 7, 2 equals 7 times 7 equals 49. When using more complex equations, which may combine several terms and use multiple operations, grouping the terms together helps organize the equation. Parentheses are most commonly used in grouping, but you may also see brackets. When a term or expression is inside one of these grouping symbols, it means that any operation indicated to be done on the group is done to the entire term or expression. Example. Solve the equation n equals 2 times 9 divided by 3 plus 4 plus 3, 2. Start with the operations inside the parentheses, then perform the operations inside the brackets. N equals 2 times 9 divided by 3 plus 4 plus 3, 2. N equals 2 times 3 plus 7, 2. First, complete the operations inside the parentheses. N equals 2 times 3 plus 49. N equals 2 times 52. Second, complete the operations inside the brackets. N equals 104. Order of operation. In algebra, rules have been set for the order in which operations are evaluated. These same universally accepted rules are also used when programming algebraic equations in calculators. When solving the following equation, the order of operation is given below. N equals 62-54. 2 plus 6 2-4 plus 3 times 8 plus 10 divided by 2 plus 25 plus 42 times 2 divided by 4 plus 3/4. 1. Parentheses. First you must do everything in parentheses, starting from the innermost parentheses. If the expression has a set of brackets, treat these exactly like parentheses. If you are working with a fraction, treat the top as if it was in parentheses and the denominator as if it were in parentheses, even if there is none shown. From the equation above, completing the calculation in parentheses gives the following. N equals 8. 2 plus 6 2-4 plus 3 times 8 plus 5 plus 25 plus 84 divided by 4 plus 3/4. Then, N equals 8. 2 plus 6 2-4 plus 3 times 13 plus 25 plus 84 divided by 4 plus 3/4. 2. Exponents. Next, clear any exponents. Treat any roots, square roots, cube roots, and so forth as exponents. Completing the exponents and roots in the equation gives the following. N equals 64 plus 36-4 plus 3 times 13 plus 5 plus 84 divided by 4 plus 3/4. 3. Multiplication and division. Evaluate all of the multiplications and divisions from left to right. Multiply and divide from left to right in one step. A common error is to use 2 steps for this, that is, to clear all of the multiplication signs, and then clear all of the division signs, but that is not the correct method. Treat fractions as division. Completing the multiplication and division in the equation gives the following. N equals 64 plus 36-4 plus 39 plus 5 plus 21 plus 3/4. 4. Addition and subtraction. Evaluate the additions and subtractions from left to right. Like above, addition and subtraction are computed left to right in one step. Completing the addition and subtraction in the equation gives the following. X equals 161 3/4. A commonly used acronym, Pemdas, is used for remembering the order of operation in algebra. Pemdas is an acronym for parentheses, exponents, multiplication, division, addition, and subtraction. To remember it, many use the sentence, "Please excuse my dear Aunt Sally." Always remember, however, to multiply/divide or add/subtract in one sweep from left to right, not separately. Order of operation for algebraic equations. 1. Parentheses 2. Exponents 3. Multiplication 4. Division 5. Addition 6. Subtraction. Computing area of two-dimensional solids. Area is a measurement of the amount of surface of an object. Area is usually expressed in such units as square inches or square centimeters for small surfaces, or in square feet or square meters for larger surfaces. Figure 3-13 summarizes the formulas for computing the area of two-dimensional solids. 3-18. Object area formula figure. Rectangle length times width equals L times W. 3-14. Square length times width or side times side equals L times W or A equals S2. 3-15. Triangle. 1/2 times length times height or 1/2 times base times height or base times height divided by 2. A equals 1/2. L times H or A equals 1/2. B times H or A equals B times H divided by 2. 3-16. 3-17. Parallelogram length times height equals L times H. 3-18. Trapezoid 1/2. Base 1 plus base 2 times height equals 1/2. B1 plus B2 times H. 3-19. Circle pi times radius 2 equals pi times R2. 3-20. Ellipse pi times semi minus axis. A times semi minus axis B equals pi times A times B. 3-21. Wing area span times mean chord equals S times C. 3-22. Figure 3-13. Formulas to compute area. Rectangle. A rectangle is a four-sided figure with opposite sides of equal length and parallel to each other. Figure 3-14. All of the angles are right angles. A right angle is a 90 degrees angle. The rectangle is a very familiar shape in mechanics. The formula for the area of a rectangle is area equals length times width equals L times W. Example. An aircraft floor panel is in the form of a rectangle having a length of 24 inches and a width of 12 inches. What is the area of the panel expressed in square inches? First, determine the known values and substitute them in the formula. equals L times W equals 24 inches times 12 inches equals 288 square inches. W equals 12. L equals 24. Figure 3-14. Rectangle. Square. A square is a four-sided figure with all sides of equal length and opposite sides are parallel to each other. Figure 3-15. All angles are right angles. A right angle is a 90 degrees angle. The formula for the area of a square is area equals length times width equals L times W. Since the length and the width of a square are the same value, the formula for the area of a square can also be written as area equals side times side equals S2. Example. What is the area of a square access plate, whose side measures 25 inches? First, determine the known value and substitute it in the formula. Equals L times W equals 25 inches times 25 inches equals 625 square inches. S equals 25. Figure 3-15. Square. Triangle. A triangle is a three-sided figure. The sum of the three angles in a triangle is always equal to 180 degrees. Triangles are often classified by their sides. An equilateral triangle has three sides of equal length. An isosceles triangle has two sides of equal length. A scalene triangle has three sides of differing lengths. Triangles can also be classified by their angles. An acute triangle has all three angles less than 90 degrees. A right triangle has one right angle, a 90 degrees angle. An obtuse triangle has 3-19. Triangles based on sides. Scalene. Isosceles equilateral. Length of all sides are di-tilde-errant. Length of two sides are equal. Length of all sides are equal. Triangles based on angles. Acute right obtuse. Each angle is less than 90 degrees. One angle is equals 90 degrees. One angle is greater than 90 degrees. Figure 3-16. Types of triangles. One angle greater than 90 degrees. Each of these types of triangles is shown in figure 3-16. The formula for the area of a triangle is area equals 1/2 times base times height equals 1/2 times b times h. Example. Find the area of the obtuse triangle shown in figure 3-17. First, substitute the known values in the area formula. Equals 1/2 times b times h equals 1/2 times 2 single quote 6 times 3 single quote 2. Next, convert all dimensions to inches. 2 single quote 6 equals 2 times 12 plus 6 equals 24 plus 6 equals 30 inches. 3 single quote 2 equals 3 times 12 plus 2 equals 36 plus 2 equals 38 inches. Now, solve the formula for the unknown value. Equals 1/2 times 30 inches times 38 inches equals 570 square inches. Parallelogram. A parallelogram is a four-sided figure with two pairs of parallel sides. Figure 3-18. Parallelograms do not necessarily have four right angles. The formula for the area of a parallelogram is area equals length times height equals L times h. Length. Height. Figure 3-18. Parallelogram. Trapezoid. A trapezoid is a four-sided figure with one pair of parallel sides. Figure 3-19. The formula for the area of a trapezoid is area equals 1/2 base 1 plus base 2 times height. Example. What is the area of a trapezoid in figure 3-19 whose bases are 14 inches and 10 inches, and whose height, or altitude, is 6 inches? First, substitute the known values in the formula. Equals 1/2 b1 plus b2 times h equals 1/2 14 inches plus 10 inches times 6 inches equals 1/2 24 inches times 6 inches equals 12 inches times 6 inches equals 72 square inches. b2 equals 10, height equals 2 feet, 6 in. Height equals 6. b1 equals 14. Base equals 3 feet, 2 in. Figure 3-19. Trapezoid. Figure 3-17. Obtuse triangle. 3-20. Circumference. B. Diameter. D. Radius. R. A. Circumference equals C equals 2 pi of 2 plus B2. 2. Pi equals 3.1416. Equals length of one of the semi-minus axes. B equals length of the other semi-minus axis. Area equals pi x at x b. Figure 3-20. Circle. Circle. A circle is a closed, curved, plane figure. Figure 3-20. Every point on the circle is an equal distance from the center of the circle. The diameter is the distance across the circle, through the center. The radius is the distance from the center to the edge of the circle. The diameter is always twice the length of the radius. The circumference, or distance around a circle, is equal to the diameter times pi. Circumference equals C equals d pi. The formula for the area of a circle is area equals pi times radius 2 equals pi times r2. Example. The bore, which is inside diameter, of a certain aircraft engine cylinder is 5 inches. Find the area of the cross-section of the cylinder. First, substitute the known values in the formula. Equals pi times r2. The diameter is 5 inches, so the radius is 2.5 inches. Diameter equals radius times 2. Equals 3.1416 times 2.5 inches. 2 equals 3.1416 times 6.25 square inches equals 19.635 square inches. Ellipse. An ellipse is a closed, curved, plane figure and is commonly called an oval. Figure 3-21. In a radial engine, the articulating rods connect to the hub by pins, which travel in the pattern of an ellipse, that is, an elliptical or orbital path. Figure 3-21. Ellipse. Wing area. To describe the shape of a wing, figure 3-22. Several terms are required. To calculate wing area, it is necessary to know the meaning of the terms span and chord. The wingspan, S, is the length of the wing from wingtip to wingtip. The chord is the average width of the wing from leading edge to trailing edge. If the wing is a tapered wing, the average width, known as the mean chord, C, must be known to find the area. The formula for calculating wing area is, area of a wing equals span times mean chord. Example. Find the area of a tapered wing, whose span is 50 feet, and whose mean chord is 6:8. First, substitute the known values in the formula. A equals S times C equals 50 feet times 6 feet 8 inches. Note, 8 inches equals 8/12 feet equals 0.67 feet, equals 50 feet times 6.67 feet equals 333.5 square feet. C. S. A equals wing area, foot. 2. C equals average chord, foot. S equals span, foot. Figure 3-22. Wing plan form. 3-21. Units of area computing volume of 3-dimensional. A square foot measures 1 foot by 1 foot. It also measures 12 solids. Inches by 12 inches. Therefore, 1 square foot also equals 144 square inches. That is, 12 times 12 equals 144. To convert square feet to square inches, multiply by 144. To convert square inches to square feet, divide by 144. A square yard measures 1 yard by 1 yard. It also measures 3 feet by 3 feet. Therefore, 1 square yard also equals 9 square feet. That is, 3 times 3 equals 9. To convert square yards to square feet, multiply by 9. To convert square feet to square yards, divide by 9. Refer to figure 3-23, Applied Mathematics Formula Sheet, for a comparison of different units of area. 3-dimensional solids have length, width, and height. There are many 3-dimensional solids, but the most common are rectangular solids, cubes, cylinders, spheres, and cones. Volume is the amount of space within a solid. Volume is expressed in cubic units. Cubic inches or cubic centimeters are used for small spaces and cubic feet or cubic meters for larger spaces. Area. Celsius equals ~times. Degrees Fahrenheit, -32. 1 pound, 16 ounces 453.592 grams 0.4536 kilograms Fahrenheit equals / above times, degrees Celsius, +32. 1 ton 2,000 pounds 1 milligram 0.001 grams 1 kilogram 1,000 grams 2 pounds and 20 pence 1 gram 0.0353 ounces. Conversion factors. Length. 1 inch 2.54 centimeters 25.4 millimeters 1 foot 12 inches 30.48 centimeters 1 yard 3 feet 0.9144 meters 1 mile 5,280 feet 1,760 yards 1 millimeter 0.0394 inches 1 kilometer 0.62 miles. 1 square inch 6.45 square centimeters 1 square foot 144 square inches 0.093 square meters 1 square yard 9 square feet 0.836 square meters 1 acre 43,560 square feet 1 square mile 640 acres 2.59 square kilometers 1 square centimeter 0.155 square inches 1 square meter 1.195 square yards 1 square kilometer 0.384 square miles. Volume. 1 fluid ounce 29.57 cubic centimeters 1 cup 8 fluid ounces 1 pint 2 cups 16 fluid ounces 0.473 liters 1 quart 2 pints 4 cups 32 fluid ounces 0.9463 liters 1 gallon 4 qu. 8 pints 16 cups 128 ounces 3.785 liters 1 gallon 231 cubic inches 1 liter 0.264 gallons 1.057 quarts 1 cubic foot 1,728 cubic inches 7.5 gallons 1 cubic yard 27 cubic feet 1 board foot 1 inch x 12 inches x 12 inches. Weight temperature. 1 ounce 28.350 grams degrees Fahrenheit to degrees Celsius to degrees Fahrenheit. Figure 3-23. Applied Mathematics Formula Sheet. 3-22. Order of operation for algebraic equations. 1. Parentheses 2. Exponents 3. Multiplication 4. Division 5. Addition 6. Subtraction. Use the acronym Pemdas to remember the order of operation in algebra. Pemdas is an acronym for parentheses, exponents, multiplication, division, addition, and subtraction. To remember it, many use the sentence, "Please excuse my dear Aunt Sally." Trigonometric equations. B. C A. A C B. Opposite side, side A. Sine, sin, of angle, A equals. Hypotenuse, side C. Adjacent side, side B. Cosine, cos, of angle, A equals. Hypotenuse, side C. Opposite side, side A. Tangent, tan, of angle, A equals. Adjacent side, side B. Formulas for area of two-dimensional objects. L equals 3. W equals 2. H equals 2. Solid volume surface area figure. Rectangle. Solid. H. Cube. Cylinder sphere. Cone. L times W times H. S3. Pi times R2 times H tilde slash times pi times R3. Slash times pi times R2 times H. 2 times W times L plus W times H plus L times H. 6 times S2. 2 times pi times R2 plus pi times D times H. 4 times pi times R2. Pi times R times R plus R2 plus H2. 1/2. 1-24. 1-25. 1-26. 1-28. 1-29. Names and symbols for metric prefixes. W. L. Prefix means. Figure 3-24. Rectangular solid. Exa. 1018. Peta. 1015. Tera. 1012. Giga. 109. Mega. 10.6. Kilo. 10.3. Hecto. 10.2. Deca. 10.1. Desa. 10-1. Centi. 10-2. Milli. 10-3. Micro. 10-6. Nano. 10-9. Pico. 10-12. Powers of 10. Powers of 10. 1 quintillion times. 1 quadrillion times 1 trillion times. 1 billion times 1 million times. 1,000 times 100 times. 10 times 1/10 of. 100th of 1,000th of. 1 millionth of 1 billionth of. 1 trillionth of. Expansion value. Pythagorean theorem. C. A. 10, 5. 10, 4. 10, 3. 10, 2. 10, 1. Negative exponents. 10-1. 10-2. 10-3. 10-4. 10-5. 10-6. 1 million. 100,000. 10,000. 1,000. 100. 10. 1. B. In figure 3-25, the rectangular solid is 3 feet by 2 feet by 2 feet. The volume of the solid in figure 3-24 is equals 3 feet times 2 feet times 2 feet equals 12 cubic feet. Example. A rectangular baggage compartment measures 5 feet 6 inches in length, 3 feet 4 inches in width, and 2 feet 3 inches in height. How many cubic feet of baggage will it hold? First, substitute the known values into the formula. V equals L times W times H equals 5 single quote 6 times 3 single quote 4 times 2 single quote 3 equals 5.5 feet times 3.33 feet times 2.25 feet equals 41.25 cubic feet. Cube. 10x 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 10. 10x 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 10. 10x 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 10. 10x 10x 10. 10x 10. 10. A cube is a solid with 6 square sides. Figure 3-25. A cube is just a special type of rectangular solid. It has the same formula for volume as does the rectangular solid, which is volume equals length times width times height equals L times W times H. Because all of the sides of a cube are equal, the volume formula for a cube can also be written as volume equals side times side times side equals S3. Positive exponents. 10, 6. 10, 0. A2 plus B2 equals C2. Figure 3-23. Applied mathematics formula sheet, continued. Rectangular solid. A rectangular solid is a three-dimensional solid with 6 rectangular-shaped sides. Figure 3-24. The volume is the number of cubic units within the rectangular solid. The formula for the volume of a rectangular solid is 1/10. 1/10x10, 1/10x10x10, 1/10x10x10x10, 1/10x10x10x10x10, 1/10x10x10x10x10, 1 divided by 10 equals 0.1. 1 divided by 100 equals 0.01. 1/1000 equals 0.001. 1/10,000 equals 0.0001. 1/100,000 equals 0.00001. 1/1,000,000 equals 0.00001. S. Volume equals length times width times height equals L times W times H. Figure 3-25. Cube. 3-23. Example. A large, cube-shaped carton contains a shipment of smaller boxes inside of it. Each of the smaller boxes is 1 foot times 1 foot times 1 foot. The measurement of the large carton is 3 feet times 3 feet times 3 feet. How many of the smaller boxes are in the large carton? First, substitute the known values into the formula. V equals L times W times H equals 3 feet times 3 feet times 3 feet equals 27 cubic feet of volume in the large carton. Since each of the smaller boxes has a volume of 1 cubic foot, the large carton holds 27 boxes. Cylinder. A solid having the shape of a can, a length of pipe, or a barrel is called a cylinder. Figure 3-26. The ends of a cylinder are identical circles. The formula for the volume of a cylinder is volume equals pi times radius 2 times height of the cylinder equals pi r2 times h. One of the most important applications of the volume of a cylinder is finding the piston displacement of a cylinder in a reciprocating engine. Piston displacement is the total volume, in cubic inches, cubic centimeters, or liters, swept by all of the pistons of a reciprocating engine as they move in one revolution of the crankshaft. The formula for piston displacement is given as piston displacement equals pi times bore divided by 2 times stroke times #sign cylinders. The bore of an engine is the inside diameter of the cylinder. The stroke of the engine is the length the piston travels inside the cylinder. Figure 3-27. D. Piston. H equals stroke. Cylinder. Piston. Piston at top center, piston at bottom center. R. H. Diameter bore. Figure 3-27. Cylinder displacement. Example. Find the piston displacement of one cylinder in a multi-cylinder aircraft engine. The engine has a cylinder bore of 5.5 inches and a stroke of 5.4 inches. First, substitute the known values in the formula. V equals pi times R2 times H equals 3.1416 times 5.5 divided by 2 times 5.4. V equals 23.758 times 5.4 equals 128.29 cubic inches. The piston displacement of one cylinder is 128.29 cubic inches. For an 8-cylinder engine, then the total engine displacement would be total displacement for 8 cylinders equals 8 times 128.29 equals 1026.32 cubic inches of displacement. Sphere. A solid having the shape of a ball is called a sphere. Figure 3-28. A sphere has a constant diameter. The radius, r, of a sphere is 1/2 of the diameter, d. The formula for the volume of a sphere is given as V equals 4/3 times pi times radius 3 equals 4/3 times pi times r3, or V equals 1/6 times pi d3. Example. A pressure tank inside the fuselage of a cargo aircraft is in the shape of a sphere with a diameter of 34 inches. What is the volume of the pressure tank? Figure 3-26. Cylinder. 3-24. Figure 3-28. Sphere. V equals 4/3 times pi times radius 3 equals 4/3 times 3.1416 times 34 halves 3 equals 1.33 times 3.1416 times 17. 3 equals 1.33 times 3.1416 times 4,913. V equals 20,528.125 cubic inches. Cone. A solid with a circle as a base, and with sides that gradually taper to a point is called a cone. Figure 3-29. The formula for the volume of a cone is given as V equals 1/3 times pi times radius 2 times height equals 1/3 times pi times r2 times h. Units of volume. Since all volumes are not measured in the same units, it is necessary to know all the common units of volume, and how they are related to each other. For example, the mechanic may know the volume of a tank in cubic feet or cubic inches, but when the tank is full of gasoline, he or she is interested in how many gallons it contains. Refer to Figure 3-23, Applied Mathematics Formula Sheet, for a comparison of different units of volume. Computing surface area of three-dimensional solids. The surface area of a three-dimensional solid is the sum of the areas of the faces of the solid. Surface area is a different concept from that of volume. For example, surface area is the amount of sheet metal needed to build a rectangular fuel tank, while volume is the amount of fuel that the tank can contain. Rectangular solid. The formula for the surface area of a rectangular solid, Figure 3-24, is given as surface area equals 2 times width times length plus width times height plus length times height equals 2 times W times L plus W times H plus L times H cube. The formula for the surface area of a cube, Figure 3-25, is given as surface area equals 6 times side times side equals 6 times S2. Example. What is the surface area of a cube with a side measure of 8 inches? Surface area equals 6 times side equals 6 times S2 equals 6 times 8 equals 6 times 64 equals 384 square inches. Cylinder. The formula for the surface area of a cylinder, Figure 3-26, is given as surface area equals 2 times pi times radius 2 plus pi times diameter times height equals 2 times pi times r2 plus pi times d times h. Sphere. The formula for the surface area of a sphere, Figure 3-28, is given as surface area equals 4 times pi times radius 2 equals 4 times pi times r2. Cone. The formula for the surface area of a right circular cone, Figure 3-29, is given as surface area equals pi times radius plus radius 2 plus height 2 equals pi times r plus r2 plus h2 h s r. Figure 3-29. Cone. 3-25. Solid volume surface area figure. Rectangle. Solid. L times W times H2 times W times L plus W times H plus L times H. 3-24. Cube S3, 6 times S2, 3-25. Cylinder pi times R2 times H2 times pi times R2 plus pi times D times H. 3-26. Sphere 4/3 times pi times R3 4 times pi times R2, 3-28. Cone 1/3 times pi times R2 times H pi times R times R plus R2 plus H2, 1/2. 3-29. Figure 3-30. Formulas to compute volume and surface area. Figure 3-30 summarizes the formulas for computing the volume and surface area of three-dimensional solids. Trigonometric functions. Trigonometry is the study of the relationship between the angles and sides of a triangle. The word trigonometry comes from the Greek trigonon, which means three angles, and metro, which means measure. Right triangle, sides, and angles. In figure 3-31, notice that each angle is labeled with a capital letter. Across from each angle is a corresponding side, each labeled with a lowercase letter. This triangle is a right triangle because angle C is a 90 degrees angle. Side A is opposite from angle A and is sometimes referred to as the opposite side. Side B is next to, or adjacent to, angle A and is therefore referred to as the adjacent side. Side C is always across from the right angle, and is referred to as the hypotenuse. Sine, cosine, and tangent. The three primary trigonometric functions, and their abbreviations are sine, sin, cosine, cos, and tangent, tan. These three functions can be found on most scientific calculators. The three trigonometric functions are actually ratios comparing two of the sides of the triangle as follows. Opposite side, side A sine, sin, of angle, A equals hypotenuse, side C, adjacent side, side B, cosine, cos, of angle, A equals hypotenuse, side C, opposite side, side A tangent, tan, of angle, A equals adjacent side, side B. Example. Find the sine of a 30 degrees angle. Calculator method. Using a calculator. Select the sin feature, enter the number 30, and press enter. The calculator should display the answer as 0.5. This means that when angle A equals 30 degrees, then the ratio of the opposite side, A to the hypotenuse, C, equals 0.5 to 1. So the hypotenuse is twice as long as the opposite side for a 30 degrees angle. Therefore, sin 30 degrees equals 0.5. Trigonometry table method. When using a trigonometry table, find 30 degrees in the first column. Next, find the value for sin 30 degrees under the second column marked sine, or sin. The value for sin 30 degrees should be 0.5. Pythagorean theorem. The Pythagorean theorem is named after the ancient Greek mathematician, Pythagoras, 500 BC. This theorem is used to find the third side of any right triangle when two sides are known. The Pythagorean theorem states that a 2 plus b2 equals c2. Figure 3-32, where c equals the hypotenuse of a right triangle. A is one side of the triangle and b is the other side of the triangle. Example. What is the length of the longest side of a right triangle? Given the other sides are 7 inches and 9 inches, the longest side of the right triangle is always side C, the hypotenuse. Use the Pythagorean theorem to solve for the length of side C as follows. A 2 plus b2 equals c2. 7, 2 plus 9, 2 equals c2. 49 plus 81 equals c2. 130 equals c2. C equals 130 equals 11.4 inches therefore. Side C equals 11.4 inches. B, C, A, C, A, B, C, B. A 2 plus b2 equals c2. Figure 3-31. Right triangle. Figure 3-32. Pythagorean theorem. 3-26. Example. The cargo door opening in a military airplane is a rectangle that is 5½ feet tall by 7 feet wide. A section of square steel plate that is 8 feet wide by 8 feet tall by 1 inch thick must fit inside the airplane. Can the square section of steel plate fit through the cargo door? It is obvious that the square steel plate will not fit horizontally through the cargo door. The steel plate is 8 feet wide, and the cargo door is only 7 feet wide. However, if the steel plate is tilted diagonally, will it fit through the cargo door opening? The diagonal distance across the cargo door opening can be calculated using the Pythagorean theorem, where A is the cargo door width, B is the cargo door height, and C is the diagonal distance across the cargo door opening. A 2 plus b2 equals c2. 7 feet, 2 plus 5.5 feet, 2 equals c2. 49 plus 30.25 equals c2. 79.25 equals c2. C equals 8.9 feet. The diagonal distance across the cargo door opening is 8.9 feet. So the 8-foot wide square steel plate fits diagonally through the cargo door opening and into the airplane. Measurement systems. Conventional, US or English, system. Our conventional, US or English, system of measurement is part of our cultural heritage from the days when the 13 colonies were under British rule. It started as a collection of Anglo-Saxon, Roman, and Norman French weights and measures. For example, the inch represents the width of the thumb and the foot is from the length of the human foot. Tradition holds that King Henry I decreed that the yard should be the distance from the tip of his nose to the end of his thumb. Since medieval times, commissions appointed by various English monarchs have reduced the chaos of measurement by setting specific standards for some of the most important units. Some of the conventional units of measure are inches, feet, yards, miles, ounces, pints, gallons, and pounds. Because the conventional system was not set up systematically, it contains a random collection of conversions. For example, 1 mile equals 5,280 feet, and 1 foot equals 12 inches. Metric system. The metric system, also known as the International System of Units, (C), is the dominant language of measurement used today. Its standardization and decimal features make it well suited for engineering and aviation work. The metric system was first envisioned by Gabriel Mouton, vicar of St. Paul's Church in Lyons, France. The meter is the unit of length in the metric system, and it is equal to 1/10 millionth of the distance from the equator to the North Pole. The liter is the unit of volume, and is equal to 1 cubic decimeter. The gram is the unit of mass and is equal to 1 cubic centimeter of water. All of the metric units follow a consistent naming scheme, which consists of attaching a prefix to the unit. For example, since kilos stands for 1,000, 1 kilometer equals 1,000 meters. Centi is the prefix for 100th, so 1 meter equals 100 centimeters. Milli is the prefix for 1,000ths and 1 gram equals 1,000 milligrams. Refer to figure 3-33 for the names and definitions of metric prefixes. Multiplier. Symbol prefix multiplier. Exponential. Numerical. Greater than 1. Exa. 10, 18, 1,000, 000, 000, 000, 000, 000, quintillion ppeta. 10, 15, 1,000, 000, 000, 000, 000, quadrillion t ter. 10, 12. 1,000, 000, 000, 000, 000 trillion g giga. 10, 9, 1 billion billion m mega. 10, 6, 1 million million k kilo. 10, 3, 1,000 thousand h hecto. 10, 2, 100 hundred deca. 10, 1, 10 10 1 unit less than 1. D deci, 10-1, 0.1 c centi. 10-2, 0.01 hundredth m milli. 10-3, 0.00 1,000th microsine micro. 10-6, 0.000 001 millionth nano. 10-9, 0.000 000,001 billionth p pico. 10-12, 0.000 000,000 001 trillionth f femto. 10-15, 0.000 000,000 000,001 quadrillionth atto. 10-18, 0.000 000,000 000,000,001 quintillionth. Meaning. Figure 3-33. Names and definitions of metric prefixes. 3-27. Measurement systems and conversions. The United States primarily uses the conventional, U.S., or English, system, although it is slowly integrating the metric system, C. A recommendation to transition to the metric system within 10 years was initiated in the 1970s. However, this movement lost momentum, and the United States continues to use both measurement systems. Therefore, information to convert between the conventional, U.S., or English, system and the metric, C, system has been included in Figure 3-23, Applied Mathematics Formula Sheet. Examples of its use are as follows. To convert inches to millimeters, multiply the number of inches by 25.4. Example. 20 inches equals 20 times 25.4 equals 508 millimeters. To convert ounces to grams, multiply the number of ounces by 28.35. Example. 12 ounces equals 12 times 28.35 equals 340.2 grams. The binary number system. The binary number system has only 2 digits, 0 and 1. The prefix in the word binary is a Latin root for the word 2, and its use was first published in the late 1700s. The use of the binary number system is based on the fact that switches or valves have 2 states, open or closed, on/off. Currently, one of the primary uses of the binary number system is in computer applications. Information is stored as a series of 0 seconds and 1 second, forming strings of binary numbers. An early electronic computer, ENIAC, Electronic Numerical Integrator and Calculator, was built in 1946 at the University of Pennsylvania and contained 17,000 vacuum tubes, along with 70,000 resistors, 10,000 capacitors, 1,500 relays, 6,000 manual switches, and 5 million solder joints. Computers obviously have changed a great deal since then, but are still based on the same binary number system. The binary number system is also useful when working with digital electronics because the 2 basic conditions of electricity, on and off, can be represented by the 2 digits of the binary number system. When the system is on, it is represented by the digit 1, and when it is off, it is represented by the digit 0. Place values. The binary number system is a base 2 system. That is, the place values in the binary number system are based on powers of 2. An 8-bit binary number system is shown in Figure 3-34. Converting binary numbers to decimal numbers. To convert a binary number to a decimal number, add up the place values that have a 1. Place values that have a 0 do not contribute to the decimal number conversion. Example. Convert the binary number 10,110,011 to a decimal number. Using the place value chart in Figure 3-35, add up the place values of the 1 second in the binary number. Ignore the place values with a 0 in the binary number. The binary number 10,110,011 equals 128 plus 0 plus 32 plus 16 plus 0 plus 0 plus 2 plus 1 equals 179 in the decimal number system. Converting decimal numbers to binary numbers. To convert a decimal number to a binary number, the place values in the binary system are used to create a sum of numbers that equal the value of the decimal number being converted. Start with the largest binary place value and subtract from the decimal number. Continue this process until all of the binary digits are determined. Example. Convert the decimal number 233 to a binary number. Start by subtracting 128, the largest place value from the 8-bit binary number, from 233. 233 minus 128 equals 105. A 1 is placed in the first binary digit space, 1xxxxxxx. Continue the process of subtracting the binary number place values. 105 minus 64 equals 41. A 1 is placed in the second binary digit space, 11xxxxxx. 41 minus 32 equals 9. A 1 is placed in the third binary digit space, 111xxxxx. Place value 2, 7, 2, 6, 2, 5, 2, 4, 2, 3, 2, 2, 2, 1, 2, 0, or 128, or 64 or 32 or 16 or 8 or 4 or 2 or 1. 10,011,001 shown as 1, 0, 0, 1, 1, 0, 0, 1 equals 153. 0, 0, 1, 0, 1, 0, 1, 1 shown as 0, 0, 1, 0, 1, 0, 1, 1 equals 43. Figure 3-34. Binary system. 3-28. Place value. 2, 7. Or 128. 2, 6. Or 64. 2, 5. Or 32. 2, 4. Or 16. 2, 3. Or 8. 2, 2. Or 4. 2, 1. Or 2. 2, 0. Or 1. 10,110,011 shown as 1, 0, 1, 1, 0, 0, 1, 1. 128 plus 0 plus 32 plus 16 plus 0 plus 0 plus 2 plus 1 equals 179. Figure 3-35. Place value chart. Since 9 is less than 16, the next binary place value, 0, is placed in the fourth binary digit space, 1110xxxx. 9 minus 8 equals 1. A 1 is placed in the fifth binary digit space, 11101xxx. Since 1 is less than 4, the next binary place value, 0, is placed in the sixth binary digit space, 111010xx. Since 1 is less than 2, the next binary place value, 0, is placed in the seventh binary digit space, 111010x. 1 minus 1 equals 0. A 1 is placed in the eighth binary digit space, 11,101,001. The decimal number 233 is equivalent to the binary number 11,101,001, as shown in figure 3-36. 3 additional decimal number to binary number conversions are shown in figure 3-36. 2, 7. Or 128. Or 64. Or 32. Or 16. Or 8. Or 4. Or 2. Place value. 2, 6. 2, 5. 2, 4. 2, 3. 2, 2. 2, 1. 2, 0. Or 1. 35 shown as 0, 0, 1. 0, 0, 0, 1, 1. 124 shown as 0, 1, 1, 1, 1, 1, 0, 0. 96 shown as 0, 1, 1, 0, 0, 0, 0, 0. 255 shown as 1, 1, 1, 1, 1, 1, 1, 1. 233 shown as 1, 1, 1, 0, 1, 0, 0, 1. Figure 3-36. Conversion from decimal number to binary number. 3-29. 3-30. Chapter 4. Aircraft drawings.